Here's another diagram. It's not one that we constructed from information we collected from our two sands. It's a very important diagram, but it's also a very complex one. But what it does show is the current speeds at which grains of a certain diameter will be transported in either wind or water. We'll start with water and then look at wind. The vertical axis gives current speed, and this is a powers of 10 scale, not a linear scale. The horizontal axis gives grain diameter. This time, the largest grains are on the right, which is the reverse of what we saw on the histograms and the cumulative frequency curve. We've shown typical grains at the bottom, drawn to scale, to help you with this. Let's see how this graph works by going on a little journey. Imagine that you are a sand grain 1,000 microns in diameter. That's 1 millimeter. You're sitting on the bottom of a stream where there's just a sluggish flow of water. This is point A on the graph. It rains upstream, and the extra water in the stream causes the water speed to rise. The water speed continues to rise, but the grain remains in the bottom until at point B, the grain begins to move and is transported. Let's change things. It stops raining and the water speed slows down. Now here's the surprising bit. The grain does not stop moving at speed B, but keeps moving until speed C, which is a slower water speed than speed B. Below speed C, the grain will not move. This is a crucial finding. The current speed needed to start a grain moving is higher than that at which the same grain stops moving and is deposited. These sorts of measurements can be carried out in laboratories, and using different grain sizes and current speeds, a pattern develops. We call the shaded zone on the graph the transportation zone. Above this zone, grains cannot be deposited, and below it, grains cannot be moved. But what about transportation by wind? Here we have a different part of the graph, and note that the current speeds on the vertical axis are much higher than those for transport by water. The same pattern emerges. For a given grain diameter, there is a speed at which the grain will start to move, and a lesser speed at which it will cease to move and be deposited. If we put both parts of the graph together now, you'll see quite clearly that the transportation zone for wind is well above that for water. In other words, a grain of a given diameter can be moved at lower current speeds by water. Much higher wind speeds are needed to move the same grain. So, we've been to the source of our beach sand, in this case the granite up on the moor, an igneous rock which consists of interlocking crystals of the three minerals quartz, feldspar and mica. And we've seen how physical and chemical weathering combine to break up these interlocking crystals into small rock fragments and mineral grains. And we've also seen how quartz, the most resistant of these mineral grains, provides us with information about how the grains have been transported, because the shapes and surface textures of quartz grains provide important clues about transportation by wind or by water. We can even use the sizes of grains to gain an appreciation of the speeds of currents that transported them. So, careful visual examination of a sand can reveal a great deal about the environment in which it was deposited. And this means we can study modern-day sedimentary environments and use our observations of these to help us interpret ancient sedimentary environments.
In this video, we've used simple observational techniques, combined those with experimental work in the lab, to give us an understanding of how modern-day sediments have been formed. If we look behind me here, you can see a slightly older sand dune. It's well on its way to being a proper sandstone. And you can even see layers in it. And they tell us that the wind was depositing the sand grains at different times. Now, we looked at modern dunes earlier on in the video. We're seeing a slightly older dune here, and we see exactly the same features in ancient sand dunes, which are millions of years old. Therefore, we've got a link between the past and the present. By looking at the present, we can begin to see what happened in the past.